Hello and welcome back. Today we hopefully will get through the rest of the graph algorithm module here by looking at two shortest distance algorithms. The first one that we're going to look at is Dijkstra's algorithm, and it's going to be a really simple presentation because it is almost essentially the same thing as Prim's algorithm, but instead of building a minimum spanning tree, you are building a minimum distance tree out from a single source vertex. The algorithm is virtually the same. That you use this priority queue, and you keep track of a bunch of information so that you can rebuild everything, rebuild the actual shortest path, and you pull stuff out of the heap, and then you potentially update things as you find better paths to your destination. So basically, the idea with Dijkstra's is it's a single source shortest path algorithm, right? That is the way that we're going to present it. It only works for a single source. It will produce a shortest path to all other vertices from a single source vertex. Right? Now, this will work for undirected graphs and directed graphs, but we're going to present it as our example with a directed case. But it'll still work on your assignment. But you have to be careful because even though it produces a single source shortest path from, say, S to T, that doesn't necessarily mean that it produces a shortest path from some other vertex X to T. You would have to rerun the algorithm for each vertex as a source in order to get the single source, the shortest path from that vertex to any other vertex. It is essentially, as I said before, the same algorithm as Prim's, but with different criteria. So with Prim's, remember we're still going to have this tree set, this fringe vertex set that these are the next things that we're going to encounter, and then these unseen vertices that are still an infinite distance away. And then we're going to, of course, make a greedy choice about which one do we include next. But instead of just looking at the tree vertices to the fringe vertices, we're going to be keeping track of the distance of, well, how did I get here? Right? What is the total distance starting from the source vertex all the way to this fringe vertex? And that's going to be our criteria for selecting the next one and updating the shortest distances. We keep track of a triple, right? That is the vertex, the distance to the vertex, the shortest one found so far, and the predecessor vertex. So we can rebuild the shortest distance path. All right. There we go. All right. Again, it uses a min heap, priority queue, whichever one you want to call it. But you do need the ability to be able to update those priorities. So let's go ahead and take a look at an example here. And for that, I'm going to go ahead and go to our tablet here. And again, it works equally well for undirected graphs and directed graphs. But what I'm going to do is I'm going to present this for a directed graph because it's a little bit more interesting. So we're going to we're going to be pushing singles here, or triples, excuse me, to our heap. So here's our heap, and it's a min heap, remember. And the min is simply going to be the minimum distance that we've found so far. And I'm going to initialize this. We're going to do the example first, and then we'll go through the pseudocode. But I'm going to initialize this, and we'll just assume that our source vertex here is going to be E. Right, as in the book here. If I note here that if I started at A, it's a sink. I can't get anywhere. So it's not going to be all that interesting to produce a single source shortest path from A. Everything is going to be a distance infinite away because you can't reach any of those vertices. Okay. So our single source vertex here is going to be E down here at the bottom left. Okay. That's where I'm going to start my searching. But before I do that, I need to initialize everything. I'm going to initialize all the other vertices. Oops. A, B, C, D, and I will put E here, but we're going to do it a little bit different. F, G, H, I, and J. All right? And again, remember I'm pushing singles here. The singles will be a vertex, the distance, and the predecessor. So in the initialization phase here, the distance is infinite for everything, and there is no predecessor vertex because I haven't been able to get there yet. So that'll all be the same. Of course, we'll update this throughout the entire algorithmic process. Infinite, no predecessor, infinite, no predecessor. The one exception here is going to be E. Because we're starting out at E as our source vertex, we do need to initialize it a little bit differently. There is no predecessor because if you start at E, how do you get to E? You stay where you are. And consequently, it has a distance of 0. Again, if you start at E, how do you get to E? You stay where you are, and it doesn't cost you anything to get there. Okay? The rest of these are all the same. And again, these are all infinite numbers. If you're doing a Python implementation, then you can use inf and make comparisons to it, or you can make it some very large number. Inf is probably a better way to go there, though. Right? Remember, we are on Piazza, and I am monitoring YouTube, so if you have any comments or questions, please feel free to post there. Okay? All right, so our first iteration, we're going to dequeue the highest priority, and since it's a min, in other words, the minimum distance element. And all of these are going to be infinite, except for that one exception, the source vertex where we started. So I'm going to go ahead and dequeue this. Right? And I'll go ahead and maintain the order up here. Right? So final triples. Okay. Once I've taken that out of the queue, I examine E, and I look at its neighborhood. I can get to B, I can get to D, and I can get to G. I cannot get to H yet, right? Because this is oriented this way. A neighborhood in a directed graph is only the outgoing edges. You can't go backwards on this edge. If it were like this, these two edges where you can go back and forth, then, or if it were an undirected graph, then you could pay attention to all of the neighbors. But in this case, I can only look at these three neighbors because those are the ones that are actually in the neighborhood. Okay. When I look at those neighbors, I look at the current values in the heap. So let's go ahead and take B, for example. It's over here, right? And I look from E. How did I get here? Well, I got there at a distance of 0. And so if I went to B, I would have a distance of 0 plus 5, giving me a distance of 5. Is that better than what I've found so far? And of course, everything is going to be better than infinite. So I will update B to be 5. Remember, that's not just 5. That is 0 plus 5, right? And what is my predecessor here? In other words, you updated this minimum distance. How did you get there? Well, I got there directly from E. Likewise, E to D and E to G here are going to be updated. I can get from E to D with a distance of 0 plus 5. So I will update D here, excuse me. 5, and you got there from E. And I'll also update E to G, right? Because I can now get there at a cost of 20. 0 plus 20, I can get there now at with a distance of 20, or a weight of 20. Right? There we go. And that concludes the first real iteration of Dijkstra's algorithm here. And let me go ahead and note these things as I am done with E, and the minimum distance paths that I've found so far are these three. And of course, that makes sense at the beginning of the algorithm because you know, you're first finding out about these. This could be this could be changed later on. I could get to G with a much better, is lesser weighted path. It's possible. Let's see if that happens. Okay. The next iteration is going to pull out the least weighted, again, this second column here, the least weighted path vertex, or triple in this case. Now I've got two of them that are 5, right? And so arbitrarily you can go ahead and break ties by lexicographic order or something like that. Let's go ahead and go with this one, B, right? That basically solidifies this path right here, right? Now when I get to B, I look at its neighborhood. That's not going to include E because this edge is oriented that way. It's not going to include D because, again, this edge is oriented that way. The only thing that it includes is A here. And I can now get there at a distance of 7. But how did I get to B? I got there at a distance of, starting from E at 0, plus 5, plus 7. So 0 plus 5 plus 7. That gives me 12. Right? If I were to go from E to B to A, that gives me a total distance of 12. Is that better than what I've found so far? Well, looking over here at A, 12 is definitely better than infinite. So that gets updated. Oops. There we go. And remember your predecessor vertex. How did you get to A? Well, I started at E, but then I went to B. And so B is my predecessor there, okay? On the next iteration, there's no need to break a tie here anymore. Instead, D is DQ'd here. And I will make a note here that I did take these two edges. Those have been solidified by these triples over here. And finally, this edge has been solidified, right? I'm never going to backtrack and and find a better way of getting to D from E, that is, right? Because the only way that that could happen is if I went out to B and then to G first and then somehow came back to D. But already to get out to G cost me 20, whereas to get to D directly would only cost me 5. To go out to B and then come back eventually to D means that I have to pay 5 plus whatever distance is out there, right? So I'm not going to backtrack and find that there's a shorter solution to D. The greedy choice property holds here, and we're not going to go through a full proof, but it's going to be very similar to the one that we showed for Kruskall's algorithm, proof by contradiction, all right? All right, I'm going to have a lot of updates here potentially because I'm looking at the entire neighborhood. Now, I'm looking at B here, but B has already been DQ'd from this heap, so I'm not going to end up updating it. Right? In fact, I don't even need to look at it. Likewise, A is still in there. I can get there at a distance of 5. How did I get there, though? Remember, I'm going from E to D at a cost of 5. That's documented over here. And I can go from D over to A at a cost of 5. So the total cost there is going to be 10. Is that better than what I've found so far? Yes. And so I update both of those elements. Right? 10 and a predecessor is now D. Again, how did you get there? I went through D and to get to A. C, F, and G might also be updated. C and F are definitely going to be updated because I have not seen them yet. So let's go ahead and update those. C and F. And again, what do I set this to? Well, I got to D at a cost of 5, and I can get to C at a cost of 20, so 25 total. And the predecessor here is going to be D. Predecessor for F is also going to be D, and the same cost. Again, 5 plus 20 gives me 25. Okay. What about G? From D, to get to D costs me 5, and to get over to G would only cost me 10, so for a total of 15. Is that better than what I've found so far? Absolutely. So to get to G, I go through D and it only cost me $20 or whatever you want to, or sorry, no, what am I doing? It's only 5 plus 10 is 15. There we go. Okay. So visually over here, that means that I decided that this path was not the best path anymore. Right? To go to D, to E, and F, and G, I would consider these paths now. Okay? The next thing to come out is, of course, going to be A. Oh, you know what? Before I do that, I'll also note here that I changed my mind that B to A, I can now get there through D, right? There we go. So I've only solidified two, let me go ahead and circle them, B and D. All right, there we go. And these are still question marks over here. Okay. Next iteration, as I was about to say, is we pull out A here. There we go. And that's been solidified. So A, and getting there from D, I'm never going to change that again. It's easy, really easy here to look at the neighborhood of A. There are no outgoing vertices, so we're done with that iteration. Move on. Right? The next iteration here, I'm going to pull out G. I'm going to DQ G. And what does that look like visually? Well, that means that I've committed to that path from E to D to G, and G is out of consideration now. I look at its neighborhood. That includes F, and that includes I. Right? All other vertices are incoming vertices. So to get to F, what did it cost me? 15 to get to G, right? And again, that's built right here, 15. It would cost me another 10 units or dollars or whatever you want to consider that to get to F. So at a cost of 25. That's no better. You can update that, break ties arbitrarily. You could also keep track of the number of edges that were required to get you there. And so between two equally weighted paths, you take one with fewer number of edges or something like that. But I'll just go ahead and say that whatever I found first, that's the one I'll stick with. So I'm not going to end up updating this one. What about going to I? Well, I've not seen I yet, so that's going to be an automatic update. What's the cost? Well, to get to G, it cost me 15. So to get over to I is going to cost me 5 for a total of 20. And how did I get there? Through G. Okay. And I will update that edge right there. Okay. Continuing. The next iteration, I will pull out the next least weighted, which is I, the one I just found. So I'll go ahead and commit to that. Hopefully I'm not making any mistakes. Let me go ahead and verify really quick. Yep, I think we're good. All right. And now I is committed, and we're done. Now look at the neighborhood here. I can go back to G, but G has already been DQ'd, so I'm not going to do that. I can go over to F. What's the cost? 20 plus 5 is going to be 25, but that's no better than what I've already found, so I won't update that. Okay. Next iteration, I'll pull out, again, 25 and 25 here. That's going to be a tie, so I'll just break ties lexicographically. I will commit myself to going to C through D. And I look at its neighborhood, but there's nothing connecting it outside of what I've already pulled out. So, next iteration, I pull out F, and I commit to that distance. And looking at F's neighborhood here, I can get to... now I can't see it, but let's go ahead and erase that. I can get to C, but that's already there, right? So I don't end up updating anything. On the next iteration, I pull these both out. Actually, I pull that one out, I pull that one out, right? And I end up not updating anything, right? Because, technically I would update from H. oh, I look at the neighborhood and I can get to E and G, but those have already been pulled out of the Q, E, and G. But I do see that I can get to J, but how did I get to H? Well, I didn't. It was an infinite distance. So it would be end up being infinite plus 10, which is the same thing as infinite, so I end up not updating it. Right? You can see here with the original graph that H and J were not reachable from E. Right? If I started at E, there's no directed path that gets me to either to H or J. And that's why they remain infinite here. So you could easily report that there's no such path, right, by keeping it as infinite or some flag value or something like that. Okay. Let's go ahead. That's the next algorithm. So let's go ahead and write some pseudocode for this now, right? Again, it's going to be looking very, very similar to Prim's algorithm. But the only difference is our criteria by which we update that triple. So the input will be a weighted graph G equals V comma E. There we go. Our output will be the minimum weighted path. And also a source vertex. We'll label that as S. Min weighted path from S to all other vertices. All right. So we're just going to output the distances and the predecessor vertices. From the predecessor vertices, you can always rebuild the path. What would that look like here? All right. So suppose that I wanted to know how to get to I. Right. So I asked the question. This is after the algorithm here. I asked the question, how do you get to I? And implicitly here from E in this case. Right. Well, you look at all of these triples over here. How do you get to I? You go through G as a predecessor. You go from, so I, how do I get to, or sorry, we start at E. How do I get to I? Right? And so I look at this triple, I start at the end, and I look at this triple here. First, not first, but before you got to I, you would go to G. So that changes my question, right? I go to G, and then from G, I can go to I. So now the question becomes, how do I go from E to G? Right? Well, I look at this triple now, G. How did you get to G? You went through D. So that transforms the question again to go from E to D, and then you go to G, and then I. Right? And you can see here how we end up getting there, right? E to D to G to I, but let's complete it. So the question now is, how do I go from E to D? I look at that triple, and I just say, oh, you just get there from E. And so that solidifies my shortest path here. E to D, D to G, and then go to I. Right? So you can always rebuild this tree over here just given these triples. Okay? All right. So we're going to have to initialize a min heap or / priority queue. Right? And we're going to have to set up like I did for all these triples over here, right? Where for each V in V, we'll go ahead and set up the distance to be infinite. The predecessor vertex to be nil or null or none or whatever. And then we'll NQ, Q.NQ, that triple. V, the distance. Yeah, we'll go ahead and go with the distance V, and then, of course, the predecessor there. Right? Now we need to take care of our source vertex. Remember, we started at E over here, and so the way that I'm going to do it here is a little bit different, maybe from the lecture notes here. I'm just simply going to update its priority. Q dot update priority of S. I want its distance to be 0, and there's no reason to update the predecessor vertex. It's just going to be nothing. Right? Oh, sorry, that should have been. Oh no, it's this is correct. Okay. I guess I am using phi here instead of a hyphen or whatever, but I'll go ahead and use phi. Okay. Why phi? Because if you start at S, you're already there. You're done, right? Okay. Now, for I running from 1 up to n, right, where n is the number of vertices, or you could just say while Q is not empty. And when you do it that way, it looks even more like prims. Because what we're going to do is we're going to dequeue one of these things for each iteration until it's empty, at which point we are done. Okay. I will have a triple here. I'll call it, let's say, X. D sub X and P sub X. There we go. And I will go with Q dot DQ. There we go. So that's the current. That was me basically taking something over here and moving it over here, right? And then looking at that triple. Okay. Now for each vertex V in the neighborhood of X, right? Then what I'll do is I'll put in here that is in the heap still. All right. Because again, we never backtracked. Once D was solidified, we never considered anything that went back to something that was already part of. We basically built a minimum distance tree here, so we're not going to consider those things anymore. For each element in the neighborhood, if so, I'll just put it as this if here. If V is in Q, and the way the distance, let's see, from X, so the weight from X to V plus the distance to get to X is less than, and here I'm going strictly less than, D sub V, then update D sub V to be that new lesser weight of X getting to V plus D sub X. There we go. And then also, of course, update the predecessor vertex. You can, basically the interpretation here is you can get to X at some distance or some weight. From X, you can go over to V with this weight. And so when you add them together, that's less than what you found so far. So you update that, and also you update the predecessor. How do you get to V? Well, you go through X. Right? And then update priority of V, DV, and then of course the predecessor vertex here, PV. Right. And you do that, I called it Q, sorry, because it is a priority queue. And that's it. When you are done with this while loop, you will output all the minimum distances, D sub V1 through D sub Vn, and all the predecessors, P sub V1 through P sub Vn. Right? And that information alone is enough to tell how, in fact, you don't even need to output the distances here because you can still look those up in the graph. All you need is the predecessors here. And then that is enough that you can rebuild these paths. Once you've rebuilt the path, of course, then you can just simply look up the distances 5, 10, 5, 5, 10, and 5 to get a total weight of 20 here, going from E to I. Right. I, where is it? Yeah. And that matches that 20 right there. Okay. And that's it. There, it's Dijkstra's algorithm. Again, it's basically Prim's algorithm, but with a different criteria for which you're choosing to go next. What does D sub V mean? I know what it's the distance, the weight, basically. D sub V is the, let me go ahead and write that here. Again, D sub V, this is the distance from S to V for each vertex here. That's why when I consider S here, I decrease its distance down to 0, because if you start at S, you stay there and don't move, and it doesn't cost you anything. Okay, it's the minimum distance. And initially, that's going to be infinite because you haven't seen anything, and then this gets updated on each one of these iteration of the algorithm. Okay. Really briefly here, what is the complexity? Well, this initialization phase here, and even the update can all be done in order n time, because everything is going to have the same priority except for this one. You can always put that at the front of your array and then just throw everything else in any old order. So this entire thing is going to be order n. I'll go ahead and write that, order n. Right. Extend that all the way down here, because you don't have to explicitly do an update priority. We iterate this loop here n times. Each time we dequeue something, which is going to be order log n, right? But of course, it's going to be diminishing, because as it gets smaller and smaller, then it's going to cost us. Then log of n decreases, so log of n actually decreases. For each one in the neighborhood, so ultimately we are going to be looking at every single edge and potentially updating the priority for every single edge. So ultimately, you can come out with basically or the same thing as prims. You can come out with order m log n, excuse me. And it can even get better if you use, I think, a Fibonacci heap instead of a binary heap. That offers a little bit more performance, at least for this particular application. Right? But for your actual implementations, I would encourage you to keep it simple. Just use a regular old heap that's provided by Python if you're using Python. All right? Okay. So another algorithm, or an alternative to this, again, if you want all pairs shortest paths, you can rerun Dijkstra's algorithm multiple times, once for each vertex as a source. Or you could do it all in one shot. The Floyd-Warshall algorithm is our first basically dynamic programming algorithm. It's a dynamic programming algorithm. Now, what does that mean? Don't worry about it. That's the next module. I'll completely explain that later on. It produces the path and distance for all pairs. Right? So if you've got two pairs here, and you can go from A to B, it also produces the shortest distance path from B to A and all the other pairs. And it does it all in one shot. So instead of running Dijkstra's over and over again n times, you could run Floyd-Warshall's algorithm just once and get all possibilities. It works. I'll talk about how it works here in a second, but it doesn't work for some situations where you might have a negatively weighted cycle. But that's just because the distance, the minimum distance between two elements is ill-defined. If I have a negatively weighted cycle, there's nothing to stop me from going around that cycle a million times or an arbitrary number of times, and my weight keeps going down, keeps going down, keeps going down. There is no minimum weighted path between those. Now, if you restrict yourself to simple paths, then you would have to modify the algorithm a little bit in order to get it But otherwise, I don't think that we're going to throw that at you on the grader or anything. You can still use Floyd-Warshalls here. We're not going to throw those situations at you. But of course, you could always use DFS or BFS to detect negatively weighted cycles. Or you could use actually Floyd-Warshalls to detect negatively weighted cycles. It keeps track of two matrices. Right? One for the minimum weighted distance and one for the successor vertex. Right? So this is a little bit different from Dijkstra's. From Dijkstra's, it kept track of the predecessor. So if I want to go from A to B, the data that I'm keeping track of is, well, how did you get to B? Well, you came from this intermediate vertex. And then I have to ask the question again, how do I get from A to that intermediate vertex X until I'm building basically the path from the tail all the way to the front. With Floyd-Warshall, it keeps track of a successor. How do I get from A to B? Well, first of all, you go to X. And then from X, how do I get to B? Then you go to Y. From Y, how do I get to B? You go to Z. So you can build paths the other way. And that's why I'm going to call it a successor vertex or a successor matrix. Okay. So let's go ahead and take a look visually as to the idea of Floyd-Warshalls. Here, I want to put it in between here. So there we go. All right. So consider two vertices here, Vi and Vj. All right. Suppose that I've found a minimum distance path so far that gets that is of distance or weighted distance d sub ij. This is the minimum weighted distance from from Vi to Vj found so far. Okay. Now I'm going to ask another question here. What if I went from Vi to, say, V1 first? Right? And then from V1, what if I went over to Vj? Those two paths are going to cost me something. So again, using the same label here, if d sub ij is the minimum weighted distance from Vi to Vj found so far, then what is the minimum weighted distance from Vi to V1? And then what's the minimum weighted distance from V1 over to Vi? I'll write those down. I, and then 1, and then this is d sub 1 to j. Right. So I have a decision to make here. If the distance from going to I to vertex 1 plus the distance to go from vertex 1 over to vertex j is less than what I've found so far, then I need to take V1 first. Okay? I can ask the same question of V2. Right? And this changes, and then these two change down here. Right? I can ask the same question of V3. Right? V4, V5, ... until I've asked the same question of all other vertices. So in general, what it looks like is if I go from Vi to V, and here I'm going to keep it general by saying Vk. The cost of doing that is going to be d sub ik and then d sub kj. So kj, all right? And all I need to do is repeat for k running from 1 up to n. Right? Now that's for one pair, I and j. So I have to repeat this process for each possible I and j. That sets up a super, super simple pseudocode here. So here's my input. It's a graph, a weighted graph G equals V comma E. And I don't have a source vertex here again because it works for all pairs. I'm going to find the shortest path from any node to any other node. And my output here is going to be actually two matrices, a min weighted distance matrix. And let me go ahead and see what I've labeled that. I think it's just going to be D. Yeah, D. And a successor matrix S. Okay. Now I will put in the notes here what these values are going to be. So D is going to be a bunch of D sub I j's, and again that's going to be equal to the minimum weighted distance from I to j, right? And S here is going to be S of ij. This is the successor vertex in the path from I to j, right? In other words, to go from I to j, you do the following first. You go from I to the successor of ij, and then you go on to j, right? Now this is might be an entirely other path. This is an edge here, and that's why I use that squiggly line, because now you have to ask, well, okay, fine, I go from I to this one, and then how do I get to j? Okay, these are just side notes to so that you not part of the algorithm. I'm just telling you what these things are going to be. So D is going to be initialized to an n by n integer matrix, or you can have fractional weights, so it's just going to be an n by n matrix. Right? Similar for S, right? So S and D are both n by n matrices. Now let's go ahead and do with an initialization here. For I, I'll use this syntax. So 1 less than or equal to I, comma j, comma, and then less than or equal to n. So let me note over here what this shorthand is actually doing. This is for I running from 1 up to n, and for j running from 1 up to n, including the diagonal, because it could be that you do want to detect negatively weighted cycles. So if you want to go from A back to itself, what is the minimum distance? Dijkstra or Floyd-Warshall algorithm here is going to tell you that it's going to end up being negative, right? It's not going to be 0, just stay there. You can actually go out and find this negatively weighted cycle and get back to where you started, but it paid you to actually do that traveling or something like that, right? But this is just shorthand. I'm going to initialize d sub ij to be the weight of going from vi to vj. In other words, this is just the adjacency matrix, and I will initialize s of ij to be j, right, for all edges for all valid edges, phi otherwise, right? And again, what's the interpretation here? The successor is going from I to j. How do you get there? So if I want to go from I to j and I haven't visited any other vertices yet, you just go to j, right? That's a direct edge there, right? That's the initialization. And then I have really simple for loops here. For k running from 1 up to n, for I running from 1 up to n, for j running from 1 up to n. Basically the idea that we just enumerated here. For each I and j, I needed to ask the question about v1, then v2, then v3, right? And that's what the outer for loop is doing, and then these two inner for loops here are running for over all pairs, right? All right, I've run out of room here, so I will go up here. Right? I will say that d sub ij, or actually no, let's go ahead and do it, be more formal here. If d sub I going to k plus d sub k going to j is less than d sub ij, right? Again, that's the idea right here, right? Then I need to take not v1, but vk first. So I will update d sub ij to be that new lesser weight, new lesser distance, and I will update my successor. Well, how do you get there? You get there through s sub I k, right? Now, why did I subscript these? Because how do you go from I to j? Well, you need to get the k that gave you this, right? The k that is realizing a lesser distance. That's the one that you want to go through first. Well, how do I get to k from I? Right? That's what that s of I k is giving you. Right? There we go. And then, of course, there's 1, 2, 3, 4 loops there. Right? And I will simply output in the end d and s. And we're done. Right? Now, this is a much harder algorithm to visualize. But let's go ahead and I'm not, because even for a small graph here, 5 vertices, you would be doing, I mean, take a look at this for loop here, 5 times 5 times 5. If I were to show this entire thing to you, I would have to show you 125 steps, basically. And I'm not going to do that. But what I will show you is, what does the initialization look like? Right? The initialization simply looks like a matrix, right? And it's all the edges. So I will associate A, B, C, D, E, A, B, C, D, E. And of course, on the diagonal here, we've got a bunch of zeros, because if you are at A, then you stay there at a cost of 0. Right? I can go from A to B at a cost of 1. I can go from A to C at a cost of 2. So that's going to be 1, 2. How do I get to D from A? There's no edge there, so it's infinite. How do I go from A to E with just a single edge? I don't. It's infinite. Right? It is directed, so I ask the questions in reverse too. How do I get from B to A? All right. Well, I don't have an edge there, so again, that's going to be infinite. I look at B's neighborhood here, and the only thing that I can get to is E and D at a cost of 2 and 8 respectively. So 2, 8, and then I can't get to C at all yet. Right? I might be able to get to it eventually, but ... Right? The full notes, the full lecture notes have all of these entries here. What I want to show is jump into the middle of the algorithm here going from k being 2 to k being 3. In other words, we're about to consider v sub 3, which by this convention here, 1, 2, 3, is going to be C. Consider this as a midpoint. Right? Okay, in other words, visually here, I'm going to update these things if V1, C in this case, is going to provide me a better distance. Let's consider A to D. Let me draw it as A to D here. Right? The distance that I found so far, and again, this is the matrix that we're paying attention to now. A to D is a distance of 9. How did we get there? Well, presumably we went from A to B and over to D on the second iteration of this. Right? 1, 9. Right? But now we're asking a question of, well, what if we went through C first? What's the cost? Well, to go from A to C, I just look that up in my matrix here. That's going to cost 2, and we can see that visually over here. So 2. What about going from C to D? That's C to D at a cost of 5. And again, visually, you can see that over here. So, is that better than what we found so far? 2 plus 7, or 2 plus 5 is 7. That's better than 9. So, we update this value right here. Right? And I'll do that by simply just erasing it and replacing it with 7. Right? Now, there's a separate successor matrix here that I've omitted. but we'll look at the end one here. But basically, that successor matrix S, with that entry, that same entry, would then get updated with C, because C is the successor of going from A to D. Right? You go to C first. So again, this gets updated, 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 and you have something that looks like this in the end. Right? I don't have the weights here of the last one. Those are in the notes if you want to see them. But otherwise, I am going to show you how you can use this successor matrix to rebuild the path. Okay. So, for example, let's go ahead and what's the most interesting example here? Let's go with A to D, the one that we were doing. All right. So, how do you go from A to D? Right. And I'll squiggly line this because that's a full path there. Right. So, A to D. I look at my successor matrix. A to D says that I need to go to B first. And so I update this. A, you go to B, and then from B, you go to D. And so my question has changed now. How do you go from B to D? Well, now you use the successor matrix again here. B, all the way over to D, you next go to E. So A to B to E. Oops. E. And then from there, you'll go on to D somehow. So the question becomes, how do I go from E to D? Right? E to D, it's simply just D. Right? So that completes my path there. Right? And if you want, you can look at the other matrix to find the total weight, and or you can then reconstruct and walk this path here and see that it's A to B. Then you go over to E, 3 so far, and then you go over to D at a weight of 6. All right? A total weight of 6. It's not at all, the reason I didn't go through and highlight the edges taken for each one of these is because well, there's 125 steps, but also you would end up essentially covering all of the edges. But just because that edge is colored red does not mean that it is used in a shortest path in any particular vertex. It's used in some vertex combination, but which one? You have to basically rebuild the path using the successor matrix. Okay. We do have enough time here. Let's go ahead and codify this. Meaning that let's go ahead and develop some pseudocode to actually build these paths. So my input is going to be a graph G, and the successor matrix S from Floyd-Warshall. All right. And my output, actually, let's go ahead and do this with a particular vertex. What do we want? Actually, V sub I, V sub J. My output is going to be a path, the shortest path, shortest weighted path, V sub I to V sub J. There we go. Okay. So I'll initialize my path here. I'll call it path. I'll initialize it to the first vertex. Well, if you want to go a path from VI to VJ, where do you start? VI, right? And I'll keep track of a current vertex here. Initially, that's going to be VI because, of course, I'm starting at VI. The idea here is that this is your initial vertex. You build your path and you add that vertex. You go to that vertex, and then, of course, you add that vertex to your path. From that vertex, you go to another vertex. So this is my current vertex, then finally my current vertex. So what I will do is I will repeat this while my current vertex is not equal to my ending vertex, V sub J. Right? Because I stop once I get to my destination. Again, I wanted to ask the question of how do I go from A to D, or in general, VI to VJ. You start at VI and you go until you hit VJ. I will update my current vertex by going to the next vertex according to the successor matrix. V sub current, comma, V sub j. Right? And then, of course, I will add that to my path. Plus equals, abusive notation here, really bad, but whatever, current. Basically, I'll annotate this, right? Append current to the end of the path. All right? And at the end, I output the path. That's it. There's the full algorithm. Okay. Really quick here. What is the complexity? Well, hopefully you can see that the complexity is k runs from 1 to n, 1 to n, 1 to n. This is clearly going to be n cubed, right? So not as good as Dijkstra's, but remember Dijkstra's didn't give us all the same information. You would have to run Dijkstra's over and over again n times in order to get what to get all pairs shortest paths. Floyd-Warshall's, you only have to run it once. So if you ran Dijkstra's n times, then you would end up getting n m log n or something like that, which you can then simplify to essentially n cubed log n. So in that sense, you don't have that logarithmic factor with Floyd-Warshall, and it's much simpler to implement, and it's just as efficient, if not more efficient, than additional runs of Dijkstra's. Okay, and it provides us our first glimpse into the next section of this course, which is dynamic programming. Dynamic programming is basically divide and conquer. But instead of a top-down divide and conquer, where you divide the problem into multiple pieces, smaller pieces, and then solve those pieces, you do it in a bottom-up manner. It's virtually the same, except for we'll look at a motivating example here. But instead of looking at it from top to bottom, like I said before, you look at it bottom to top. You look at the small solutions first, and then you look to see how you can combine those small solutions into larger and larger solutions until you get to the solution that you're looking for. Not only that, but you use memoization. Remember that memoization is basically caching values. You do recursion, but you also save off and cache values so that you don't have to repeatedly recompute them over and over again. The quintessential example is, of course, the Fibonacci sequence. If you were to actually do that naively, recursively, you would end up doing the same operation billions and billions of times. Whereas if you just did that one operation once, you stored it into a table, and then you looked at the table and you used that value instead of recomputing it using recursion, then you can cut out basically this huge exponentially sized tree into a polynomially sized computational branch or something. The idea of dynamic programming is that it uses memoization, but it uses it by throwing out the recursion. It uses a table and it builds up this table based on the bottom-up kind of principle. Okay, and we'll look at an example next time with binomial coefficients. All right. I see no questions, so have a good day, and I will see you in office hours.